Hi everyone. Now we'll discuss unit number 6, that is mixed signal systems for MS430. The unit name is MS430 Mixed Signal System, which carries 15 marks in external exams. Now we'll discuss all the solution for the questions which are asked in the question bank. Question number 1. Explain the operation of MS430 comparator A, or the same question asked in another way. Explain the architecture of MS430 comparator A with a block diagram, or one more format they are going to ask. Explain the architecture and operation of MS430 comparator A with block diagram. Okay, ask for 10 marks. Now I have given the block diagram of comparator A plus, okay, and it has some of the bits and to control its operations. Here you can see that you have the input is analog comparator, compares the voltages on its two input terminals V plus and V minus. Next, its output is high if V plus is greater than V minus. You can see in the diagrams you have different comparator inputs, CA0, CA1, CA2, and you have for port P2, CA3, and CA2, CA1, comparator CA1 to CA0, that is given input to the next comparator V plus and V minus. Depends on that. This provides basic bridge between the analog and digital domains, acts as a 1-bit ADC. And here you can see that the analog comparator compares the voltages on its two input terminals and V plus and V minus. Its output is high if V plus is greater than V minus, and output is low if V plus less than V minus. Thus it provides the basic bridge between here. The performance of all analog peripherals depends heavily on the capabilities of analog CMOS switches, and there are main features of comparator A plus are listed now. You can see that the entire model is switched on or switched off with the comparator on bit. Depends on the bit, you can make it on and off. It is off by default to save the currents. That means by default it is in off condition. The non-inverting input of VV plus, you can see that here in this diagram carefully to analyze this how it works. Next is can be connected to the external signals CA0 to CA2. This V plus is connected for input signal CA0 to CA2, that's V plus. Next, or left without an external connections, this is selected using the bits of P2 CA4 and P2 CA0. Okay, here you can see that P2 CA4 and P2 CA0. The strange allocation of bits maintains the compatibility with a comparator A, which had only one external input to each terminal of the comparator. An internal voltage reference can also connected to the V plus. Here the reference voltage, comparator reference voltage also is connected to the positive terminal of V plus. Similarly, the inverting input V minus can be connected to the external signals CA1 to CA7, but not CA0. You can see that here no CA0, it's connected CA1 to CA7 to the V minus terminal of the comparator. Here according to that, you can see that according to the bits P2CA, that 1:3 can also be connected to the internal references. This is internal reference voltage is connected. The internal reference voltage VK reference can be chosen for 1/4 VCC or 1/2 VCC, or nominally fixed voltage from the transistor or feed diodes. This is selected with the comparator reference bits. and it can be applied to either input of the comparator according to the comparator selection bit. The output is brought to an external pin is comparator output. It is also connected internally to capture input CCI1B of timer A, which allows precise timing without delays that would be introduced if software were needed for the communication between the models. The question number 3 is describe how we can use comparator A in capacitive touch sensing. Here you can see how our comparator is going to work in touch screen. If you press one any touch screens using finger, how it is going to work. You can see in the figure, the first one, isolated touch sensor using the capacitor field, that is electric field lines is going to generate between the insulator and conducting. Touch sensor with finger, once you press the finger which is connected to the register of through register to the MS430. The sensor works by detecting the change in capacitance when a finger is brought over it. So before using the finger, you can see that the capacitance value. After putting the pressure or after putting the finger on the touch screen, there is change in capacitance. You can see in the above diagram. Here the capacitor is formed by two conducting pads on the bottom of the insulating sheet. The pads are oftenly no more than the enlarged tracks only on a printed circuit board. It's a PCB with the board itself acting as the insulator, that is a dielectric media between the plates of the capacitor. And here we can assume that one pad is connected to the ground, other act as a sensor, but more complicated configurations are often used in the practice levels. That is, electric field is created whenever the voltage is applied between the plates and field lines go from one plate to another. Some of the lines remain in the insulator, but others emerge into the air. It might have an area of 10 mm square with a width of 2 mm between the plates. The dielectric constant of PCB is epsilon naught, that is permittivity is equal to 4. So capacitance is roughly calculated by using the formula C is equal to epsilon or epsilon naught A divided by D. Approximately it is going to give 2 picofarad. Next question is explain the basic operation of ADC10 or 5 marks, or sometimes they are going to ask explain the basic operation of ADC10 and ADC12. Both are analog digital converters, and these are going to give the digital outputs by converting the analogs. Here for ADC10, the basic hardware of the ADC10 is mainly consist of triggering from the hardware and the data transfer controllers. Here you are need 3 steps to make single conversion with ADC10, and assume that default reference for VSI and VCC are suitable, so that you need not to worry about the settling the time of reference or buffer. Operation is how it is going to convert. You will see here is configure the ADC10 including ADC10 on bit to enable your ADC. The enable bit must be clear during the operation because most bits in ADC control registers 0 and 1 can be changed only the ENC is equal to 0. The set the ENC bit to enable the conversion. That ENC means to enable the conversion. This cannot be done while model is being configured in the previous step. And third step is trigger the conversion. One is conversion started either by setting the ADC10 start conversion bit or by edge from the timer A. Out of 2, if you get any one, so it conversion is going to start. So once conversion is started from the ADC10, the last 2 steps again repeated for each conversion, and it requires again clearing and setting the enable conversion bit again. This is going to continue happens to control and to convert your values analog to digitals. Here the main reasons to perform 2 steps in ADC10 is it can be triggered either from the timer A or not from the software. A conversion should not start until the old one has been processed and conversion enabled by the toggling the ENC. Next, explain the basic operation of ADC12. Then we will see now how ADC12 is going to work. The successive approximation core and choices of inputs and clocks and triggering the sources are much same as ADC 10, but the output of ADC 12 is 2 bits or more compared to ADC 10. Output of ADC 10 is going to give digital values in the 10 bits, but in ADC 12 we will get the 12 bits rather than the 10. The internal voltage reference requires external storage capacitors. This takes a long time to charge after a reference has been turned on, and 17 milliseconds should be allowed for the voltage to stabilize. And finally, it is configured ADC 12 by using bits of SH T0 X bits and to set up for a sampling interval of 250 cycles of ADC 12 clock. And the internal reference voltage is left at 1.5 volt by default, but neither the reference nor the core of ADC 12 is turned on. Clock is taken from the internal clock oscillator for ADC 12 OSC without division. Directly we are going to take the clock from the internal oscillator. Then how it is going to perform the operations? The process for each reading starts with an interrupt from basic timer 1. Voltage reference is turned on the ISR, and watchdog timer is configured to give the further interrupts after 16 milliseconds. The reference voltage should be stable by the time of interrupt from the watchdog timer. So ADC 12 is turned on now. Now new reading is enabled and triggered. Finally, interrupt is going to occur to when conversion is complete. That indicates the conversion of analog to digital is completed. So ADC 12 has to be turned off. That is going to done by using the interrupt. So interrupt is going to set all the flags with the ADC 12. Then finally, to make the ADC 12 is turned off. Whenever it is necessary, this step is very necessary to clear the interrupt request, even though only one source is active. Now we'll see the explain the control registers of comparator A. You can see in this diagram how comparator A control register is going to work. You can see that 8 bits of comparator A control registers 1. You have two registers, comparator A control register 1, comparator A control register 2. Here you have different bits, that is first we'll see the bits. 7th bit is CAX, means comparator exchange. It is exchange the comparator inputs and inverts the comparator output. Next, 6th bit is CRSCL, that means comparator A reference selection bits. It's going to takes different values. If enable CAX is 0 and CAX is 1 at different states, how comparator selection is going to happen. For 0, VK reference is positive terminal. For CX 0, for CAX is 1, VK reference is negative. For comparator selection is 1, for comparator exchange is 0, VK reference is negative, and comparator exchange is 1, VK reference is positive. Like this, it is going to change the voltage levels. Now we'll see the comparator A voltage reference. What are the different comparator A voltage references are available? For 0 0 external, the internal reference is off, and for 0 1 it takes 0.25 volt of VCC, 1 0 0.5 volt of VCC, 1 1 0.55 volt of diode reference voltage. Next, CA on bit, it's third bit, that is comparator A becomes on when CA on is equal to 1. Next, comparator A interrupt edge. If it is 0, rising edge is going to use. If it is 1, falling edge is going to select. Next, first bit CAI comparator A input enable when CAI is 1. It enable the comparator A interrupt. Next one, comparator A interrupt flag. If it is 1, the interrupt is pending. Next one, control registers of comparator A. Second, the all 8 bits you can see in diagram. It has different bits for 4, that is P2 CA1, P2 CA0, CAF and CAout. CAout is a comparator output. CAF means comparator output with a filter is enabled when CAF is 1. Then P2 CA0 means pin is connected to CA0 when P2 CA0 is equal to 1. Again, P2 CA1 means it is connected to the P2 CA comparator analog input 1 whenever it is 1. Next one, explain the architecture of MS430 ADC10 with block diagram. They are asked this one for the 10 marks. Or you can get same question another way. Describe how you can use a ADC10 in temperature sensor. Here how the ADC is going to convert your analog to digital values. You can see the diagrams. It takes the analog inputs using the channels for A0 to L1 and it is passed through the sample and hold circuit. Finally that is passed through the successive approximation 10-bit core which taken the different reference voltage levels from the V reference and VSS and VCC negative as well as positive voltages of references, and it is given from the voltage references which having the value 5 voltage passed through the buffer which having the ADC10 SR registers, and input for sample and hold circuit it is going to get 10-bit successive approximation core which takes the different clocks from the ADC10 oscillators. Here you have the different clocks. It is going to select any clocks, divides the by 1 to 8, that is given to the input 10-bit SAR which give the output 10-bit successive approximated, that is result is going to store into the ADC10. So in sample and hold circuit, if you want to start the conversion, you have to enable the conversion using the ADC10 start conversion bit. Using that conversion is going to start, and after that the finally using temperature sensor you are connected here, that is going to give the different values of the different temperatures. The output is going to generate it on output 0, output 1 and output 2. That is the explanation I have done here. The temperature is going to calculated using the formula for 3.55 theta plus 986 is equal to, so 3.5 theta plus 278 millivolt. Theta values you have to substitute and it gives the different degree Celsius. So that is finally going to calculate the values. Here the after calculation, there we can say that the coefficient is also an significant tolerance quoted as 3.5 plus or minus 0.1 millivolt degrees per degree Celsius. So it is no surprise that the data sheet warns you that you may need to calibrate the sensors. This requires one reading at a known temperature in the range of interest, which fixes the offset. Better calibration at two temperature determine the both offset and slopes. Next we'll see describe the timing and triggering options of ADC. How your ADC is going to triggered and what will be the timing diagram for your ADCs. This is you can done by using the timer registers through the interrupts by using the output signals. Here we can use that channel 1 in timer A drives the pulse width modulation. Therefore, it is produced periodic output 1 signal which can be routed to the ADC10. It can also request the interrupts. Unfortunately, there are some problems with duty cycle. It may will get, if it is 0, will get some other type of problems. If it is 100% also, it will get. Now we'll see the problems. The output becomes constant in both cases. So there are no edges on output 1 to trigger the ADC10. So finally interrupts also cease with a duty cycle of 100%. So that does not work either. And here you have to use some interrupt service routine flag, that is called when TR counts to TSCR 0, and conversion and copy the result during a single cycle of timer clock is equal to master clock's SMCLK divided by 8. Instead of that, the ISR copies the previous converter value into TACCR1 for the next cycle of PWM. It is then insert the new conversion whose output is used in the next ISR. That is the related to the timing and triggering. Next, question number 11. Explain the control registers of ADC10. Then what is the triggering method? Let's continue part, and you have seen now here. Next we'll see the control registers of ADC10. How the control of ADC10 is done. Here you can see in the diagrams, it's by using hardware and software you are going to trigger the ADC10, and after that it is going to perform the conversion. That is for every enable conversion, repeated conversion is going to happen. You can see the conversion sequence 1 is equal to 0 divided by MSC is equal to X. Here 1 C1 sequence, conversion sequence, MS is 0, MS is 1. So single conversion individually triggered. Next repeated conversion individually triggered. Here multiple conversion only first triggered. First time only you have to trigger. The multiple conversion is going to happen in ADC10. So it selects the 3 bits control. Okay, here how they are work in hardware triggering, it's a little different than the ADC10 start conversion. Instead of doing the software, how the hardware triggering is going to happens. Consequence 0 selects between single input channel 0 or a sequence of input channels 1, and consequence 1 selects between single conversion 0 and which of must enabled by the toggling the enable conversion or repeated conversion where only the one trigger is needed for each time. And finally MSC selects whether the each conversion should be individually triggered or they should follow the each other as rapidly as possible without waiting for further triggers. After the start of the sequence, the sequence of input channels is selected, which is a consequence bit of 0 and 1. So what happens in ADC10, first it converts the input channels, then it's selected by the input channel 6, then decrements the channel until it reaches A0 and will not go for every time to trigger. And here finally we want each conversion to be triggered by the output 0. So MSC you have to keep it 0, and we don't want to toggle enable conversion before each conversion. So therefore finally you have to set the conversion sequence is 1 for repeated conversions. So this is the end of your 6th unit. After watching this video, if you get any doubts and if you get any questions other than this one, so ask me, I will clarify. Okay, thanks for watching this video. Thank you.